Advanced comfort, smart freshness டெக்னாலஜியுடன் அது துணிகளை வைக்கும் ஃப்ரெஷ்ஷாக சூடான நாட்களிலும். சிறந்த டீ சரியான விலையில் கிடைப்பது கஷ்டம். டாடா டீ கனந்தேவனில் ரெண்டுமே கிடைக்கும். இது கனந்தேவன் தோட்டங்களின் டீ. ஸ்மார்ட்டாக வாங்குங்கள் கனந்தேவன் டீ.
யூடியூப்ல பின்னாடி போடுறதா சப்ஜெக்ட் இருக்கு.
யாருக்கு வேலை கொடுத்தாரு? ஹலோ, ஓப்பன் சிட்டி ஸ்கூல். பேச அப்படி நான் உங்களை யூடியூப் ஆன் பண்ணுவேன். நான் மெயில் பண்ணியிருக்கேன் பாருங்க.
சார் கேட்குதா சார்?
அதில் இருக்கும் பாருங்க, அந்த லிங்க்லேயே அந்த அட்ரஸ் பண்ண நாட் வந்துட்டு இருக்கும் பாருங்க. கீழே இருக்கும். அதில் இருக்காங்க.
சார் கேட்குதா? சார் பேசுகிறது கேட்குதா சார் கிளியரா? சார் பேசுகிறது கேட்குதா சார்? சார் கேட்குதா?
இல்லை, கேட்கவே இல்லை.
சார் நீங்கள் பேசுகிறது எனக்கு கேட்குது சார்.
கேட்குதா?
கேட்குது சார்.
இப்போ இருங்க, சவுண்ட் வைக்கிறேன் நினைக்கிறேன். அது ஸ்பீக்கர் இது சவுண்ட் பண்ணுறது. ஹலோ
சார் கேட்குதா பேசுகிறது?
கேட்குது. நாங்கள் பேச கேட்குதா?
கேட்குது சார்.
நம்ம யூடியூப்பில் பாருங்கள், அப்படியே அது கேஸ் யூடியூப்பில் பாருங்கள். நான் சொல்லுங்கள்.
லைவ்ல கேட்குது சார். அது ஆஃப் பண்ணிடலாம் சார். இந்த 3 மட்டும் தான் சார்.
ஓகே. இப்போ இதில்
அதில் தான் சார்.
இதுவா?
எஸ் சார்.
ஓகே.
தள்ளி போய் கேட்கலாம். வெங்கடேஷ் கேட்கலாம். வெங்கடேஷ்.
சார் அந்த லிங்க் திரும்ப
வெங்கடேஷ். சார் கேமரா ஆஃப் பண்ணிங்க சார். ஓ அதை பார்த்து சரிங்களா? ஓகே சார்.
இதெல்லாம் வீடியோவில் ஓடிட்டு இருக்காப்பா. லைவ் ஸ்ட்ரீம் எல்லாம் கட் பண்ணுங்கப்பா.
ஸ்ட்ரீம் லிங்க் யாருக்கும் போடல சார். நான் இல்லை அது இது வேறு லிங்க் சார்.
எப்படின்னாலும் ஓகே தான். இன்னொன்று ஃபார் எக்ஸாம்பிள் ஓவரால் ஃபீட்பேக் சப்மிட் பண்ணதுக்கப்புறம் அவங்களுக்கு வந்து அப்படியே சர்டிஃபிகேட் கிடைக்கிற மாதிரி வந்து பண்ணா நல்லாயிருக்கும். அது ஒன்ஸ் தி கிளிக் சப்மிட். ஏன்னா ஒரு சில இதெல்லாம் வந்து பார்த்தீங்கன்னாக்கா அந்த சப்மிட் பண்ணும்போது யார் சப்மிட் பண்ணாங்களோ அவங்களோட நேம் ஷீட் எல்லாம் வந்து அந்த சர்டிஃபிகேட்டில் போய்
சம் பார்ட்டிசிபெண்ட்ஸ் வந்து இந்த செஷனுமே அட்டன் பண்ணல சார்.
எக்ஸ்டர்னல் பொறுத்த வரைக்கும் பணம் கட்டினதால அட்டன் பண்ணாலும் கொடுத்துருக்காங்க. வேண்டாம் சர்டிஃபிகேட் அட்டனன்ஸ் பிடிக்கும். எக்ஸ்டர்னல் பார்ட்டிசிபெண்ட்ஸ்க்கு
நீங்கள் வந்து உங்களோட அட்டன்ஸ் இல்லைனாலும் வந்து அவங்க வந்து நாங்கள் யூடியூப்பில் பார்த்தோன்னு சொல்லி சொன்னாங்கன்னாக்கா என்ன பண்ணுவீங்க? ஒன்றும் பண்ண முடியாது.
ஆனால் அதுலேயே ஸ்க்ரீன்ஷாட் எடுத்து வச்சுருக்கோம் சார். அதுலேயே ஸ்க்ரீன்ஷாட் எடுத்து வச்சுருக்கோம்.
ஸ்க்ரீன்ஷாட்னா எத்தனை பேர் பார்த்தாங்கிறது தெரியுமா?
ஒரு 30 பேர் அந்த மாதிரி வரும் சார்.
அப்படியா?
ஒவ்வொரு நாளைக்கும்
சார் ஆக்சுவலாக வந்து குரூப்லேயே வந்து அட்டெண்டன்ஸ் போட சொல்லியிருக்கோம். ஃபார் எக்ஸாம்பிள்
ஆக்சுவலாக செக் பாயிண்ட் வைக்க முடியும்னா ஒரு தடவை வச்சு அவங்களை கெஞ்ச விடுங்க.
அதான் சார் தான்
கொடுக்க வேண்டாம்னு சொல்ல, ஒரு தடவை கெஞ்ச விடுங்க. சர்டிஃபிகேட்டுங்கிறது ஜஸ்ட் லைக் தட்டுங்கிற மாதிரி வந்து அந்த மாதிரி ஒரு இது இமேஜை க்ரியேட் பண்ண விடக்கூடாது. நீங்கள் எதுவுமே 5 நாளுமே அட்டன் பண்ணல, அதனால் அப்சர்வேஷன் வந்துட்டு சம் பார்ட்டிசிபெண்ட்ஸுக்கு வந்துட்டு என்னன்னாக்கா சர்டிஃபிகேட் தரதுல இஷ்யூ இருக்குது. யூ டாக் டு அவர் ஹெச்ஓடிஸ்னு சொல்லி போட்டுருங்க. ஏதாச்சும் போடுங்க, அதுக்கப்புறட்டுக்கு பார்த்துக்கலாம்.
சார் இவ்வளோ இருக்குது சார். அட்லீஸ்ட் ஒரு செஷன்லாம் அட்டன் பண்ணியிருக்காங்க சார். சில பேர்லாம் வந்து 2 செஷனுமே அட்டன் பண்ணாமலாம் இருக்காங்க. இதில் யூடியூப் மட்டும் இதில் ஆட் பண்ணலாம். இதில் யூடியூப் ஆட் பண்ணியாச்சு சார். இதில் யூடியூப் மட்டும் ஆட் பண்ணணும். பண்ணால் அரௌண்ட் ஒரு 10 வந்து பில் செஷன் போகும். சொல்லுவா. ஆமாம் என்ன டாக்குமெண்ட்டு இல்லைப்பா, அது அங்கே இவங்க எப்படி பிளான் பண்ணிக்க தெரில. ஆமாம் பாருங்க. ஆமாம் ஆமாம்.
இது வந்து அவங்க அட்டனன்ஸ் என்டர் பண்ணதானே?
ஆமாம் சார். அவங்க என்ட்ரு பண்ணுறேன்.
அவங்கள்ட்ட
பேசி
என்டர் பண்ணலன்னு சொன்னேன் என்ன பண்ணுங்க?
அதான் குரூப்பில் மெசேஜ் போட்டேன் சார். யூடியூப்பில் அட்டன் பண்ணால் நான் வந்து இது மாதிரி போட்டேன்.
யார் யாருன்னு பாருங்க. எந்த காலேஜும் லிஸ்ட் எடுங்க பார்ப்போம், அதுக்கப்புறம் டிசைட் பண்ணிக்கலாம்.
இப்போ அட்டனிங் த்ரூ யூடியூப் லைவ் கைண்ட்லி என்ட்ரி யுவர் நேம் அண்ட் காலேஜ் நேம் அண்ட் லைவ்.
இல்லை, அது நீங்கள் போட்ட மெசேஜ் பார்த்துட்டேன். அதனால தான் இந்த இதை எல்லோரும் என்டர் பண்ணியிருக்காங்க, ரைட்டு. பட் ஆனால் வந்து என்னன்னாக்கா ஒரு சிலர் அட்டன் பண்ணி சோம்பேறித்தனமாக வேணுக்குன்னு என்டர் பண்ணாமல் கூட இருக்கலாம். அதனால தான் எடுத்திங்கனாக்கா அவங்க டாக்டரேட் லெவல் பெரிய லெவலாக இருந்தாக்க அவங்கள்ட்ட இது பண்ண வேண்டாம். ஜூனியர் லெவலாக இருந்தால் இடம் பொருள்
ஃபுல்லுன்னு சொல்ல என் கிளாஸில் 7 பேர் 7 பேர் 4 பேர் இருக்காங்க சார். கேர்ள்ஸ் மட்டும் உடம்பு போயிட்டாங்க.
ஓகே. அதர் செக்ஷனு
அப்படி அவர் இது பண்ணலை, நானும் சொல்லுவேன்.
அதர் செக்ஷன் யார் யார்?
சிந்தாமணி அவங்க செகண்ட் இயர்
தேர்ட் இயர் நான் தான்.
அதுதான் அவர் கேட்கல சார்.
சிந்தாமணி எங்கே இன்றைக்கி இல்லையா?
அவங்க இதுலேயே லேப்லேயே கோச்சிங்.
ஓகே.
அவங்களோட ரோட்டுக்கு எப்படி சார் சொல்லியிருந்தாங்க. சரி கேட்டால் சொல்லிக்கிறேன், நான் எப்படி சொல்கிறேன்.
ஓகே.
சரி சார், அப்படியே நான் பஸ் மெடிக்கல் பஸ்
சரிங்கப்பா, தேங்க்ஸ்.
சரி சார். சார் உங்கள் கார் இருக்கா? சரி.
லிங்க்கை இது பண்ணணும். லிங்க் வந்துச்சு, ஐடி லிங்க் வாட்ஸ்அப் அனுப்பிச்சுடுங்க. அது அப்படியே இதில் போட்டுவிடுங்க, குரூப்பில் போட்டுவிடுங்க. சரி, இப்போ கூட நான் இருந்தேன், ஜாயின் பண்ணிவிட்டேன்.
6:45 போடுறேன். 6:46 போல கொஞ்சம் ஏறணும் போலவா பண்ண முடியலன்னா நமக்கு வேணும்.
ஆமாம்,
It's almost 35. கேக்குதா? ஓகே. Yeah. So, very good evening to one and all gathered through online for day 6 FDP. So, I'm not going to invite others. So, I'm the one going to present for today's session. So today's session, right, it's about the current research work and the future directions. The purpose of this organizing this FDP is, right, a person who is interested to do research in quantum computing. So first they need to understand what is a basic thing, why we go for a quantum computing from classical to quantum, and then the basic layered architecture, and then afterwards uh, what are the building blocks, so how this can be realized through simulators or through real-time implementations, and then what are the challenges, so gates and other physical architectures, and then what are the challenges with that is it's decoherence, that especially on quantum error, quantum encoding and quantum error, and then we are working towards to provide the solution, optimized solution. So initially we started with the quantum optimization algorithm, and then that was taken by Pallavi Soni, and the basic things was taken by Ms. Aarti. And then quantum, how it can be realized, implement a small qubit, single qubit, as well as 2-bit quantum Fourier transformer. It was explained by Mr. Karthik Ganesh, and then quantum machine learning algorithm for various applications. That was again taken by Ms. Aarti. And then quantum security part, because quantum security is a major concern, because right, when we once the quantum is get evolved, sometimes the intruders now itself they take the dump whatever the data, and then they do the post analysis. Once the quantum evolved, they would be able to do the analysis, and they can identify the pattern and do security challenges. So for that, security part was quantum, post-quantum security, and PQC and QKD. So these are all taken by Dr. Darshana Upadhyay. So these are all the major part in quantum computing. So here today's my session, right, it would be like I'm going to give it in a nutshell. It's like refreshing the content, as well as what are the current research works going on and what would be the future research. So once you have understand the basic concept, and then started giving the small implementation, and then finally what are the things we can do research. So the main purpose is the teaching community as well as the researchers have to get benefit for providing the new solutions. So that's the purpose. So today we are moving on to our session. So would you be able to see my slides, presentation slides? Are you able to see?
Yes,
Okay. So I'm moving on. So this is the outline of today's presentation and this agenda. The first part is it's like a recap of quantum computing and the quantum simulation tool. So how the quantum was, why it is given more important, and how the quantum works. So that and all. And then once we know this, then we need to understand how it is being realized through simulations or real-time implementations, how it is being realized. So what are the major breakthrough till now it's going on. So if we know that, then only we will think of like how we can implement in the simulators, because when we have a real-time data, then only we can go for a real-time implementation and provide solution for it. So that's the purpose. Simulation tools are much important to like understand. And then now we are not going to talk about simulation. What are the tools are available only. So next, the part is its current research and future directions on quantum encoding and error correction. Here I'm not going to concentrate much on encoding part. So various encodings are there, but because of the coherence and decoherence of while decoding part, right, at the time error correction is a major challenge or the bottleneck for realizing the quantum. Otherwise, right, by the time the quantum will dominate in this world. So next is the quantum algorithm, and mainly optimization into it was thing. In quantum algorithm, first thing is quantum optimization algorithm, and then quantum machine learning algorithm, and then quantum communication and cryptography. And some of my undergrad students, they worked on quantum research, and I think some of you guys, people heard in the last session, we presented our work with the Canadian research peers. Dr. Darshana Upadhyay is also one of the peer member. While my students presenting, there are 3 papers. It was presented. One is on portfolio optimization, and another one is on bit error correction, and another one is on quantum security. So bit error and bit error is little bit theoretical implementation only, and as well as quantum security is also up to the level of literature study only. So the major implementation part was done for portfolio optimization, and that was going to be presented my undergrad student. So why quantum computing and research is right now trend? Hope you know everything. I'm not going to explain much, because CPU is right now used for sequential and latency sensitive applications, especially for normal regular applications. No need to say about much. And next is the GPU. GPU, right, single instruction, multiple things. So we would be able to realize, especially on graphical part. A graphical part means when it is a image based or video based, CPU cannot realize for any machine learning or generative AI applications. So at the time, we barely depend on the GPU part. Apart from that, supercomputers are very limited, even throughout the countries. Any country have limited number of supercomputers only they have. Very costlier. So we will be able to realize. But however, when the quantum computer evolves, it is possible to like do whatever. Even it will go dominate even better than the supercomputer. So that's what nowadays quantum computing is getting popular, and the research is right now it's in trend. So just a recap. So very beginning, Aarti told, hope you guys remember. So the quantum computing is the use of the principle of quantum theory, and it explains the behavior of energy and materials on atomic part, how moving from one state to the another state. So it uses the subatomic particles such as electrons or photons and quantum bits or qubits that allows this particle to exist in more than one state, zero state or one state. And similarly, a qubit is like a 2-level quantum system where the 2 basic states are usually written as. This is a basic simple 2 classical bit can be encoded as 1 qubit quantum. So here qubit can be in the state of either 0 or 1, unlike a classical bit. And finally, the superposition phenomena is being applied to get the qubit. So this is the graphical representation of the qubit. So when you see classical bit, it like zeros and ones. So when it goes to the Hamilton sphere, right, how it can be encoded either in 0 state or in 1 state. And so thereby, with the superposition principle, we can add both, and we can call it as a single qubit.
So the quantum bits, when we go for like a n bit, if it is a 8 qubit, 16 qubit, then 8 classical bits are being encoded in a different positions. So that can be positioned in the Hamilton sphere. So based upon that, the principle. So this is a graphical representation, and finally, this is what how the quantum computer evolves. In a layered architecture, right? This is about the physical physics principle and how the quantum mechanics works. So with that, we already know that either in 0 state or 1 state based on the quantum mechanics. And then it's like qubit is a unit of information, and these can be implemented or realized through the quantum gates. That is a unit of processing. How many gates are there? Based on that, that's a unit of processing. And with that quantum circuit, the algorithms are being evolved, and finally the the instructions are given for the quantum circuit for processing the given data. So that's the various applications, quantum machine learning or cryptography and so on. So this is how the quantum computer works in a layered architecture. So next we are moving on to the quantum simulation tools. So actually the simulation tools, right, it to be broadly classified into two categories. One is on software simulator, which runs on a classical computer to mimic the quantum behavior. And the next one is a hardware platforms, which offers the physical quantum resources. So at the very beginning, you would be able to see the quantum picture, right? That's one physical architecture. So it would be very complex. So if a problem, right, if it is too large for the local computer, it's very difficult to realize in a local computer. So then you have to access through the cloud simulators. So the cloud simulators are also being offered by some of the companies. So when your application it's a very bigger application, then you have to select based upon the application, right? Like you have to, and moreover, I think Hope Aarti, when she talked about quantum machine learning, she told that based on the number of parameters, you would be able to select the qubit size. So when the qubit size greater than 30, you have to go with the cloud-based architecture. So first we see about the hardware platforms. The hardware platforms are Amazon bracket, and it's a hardware agnostic hub, and it lets you to write the code and run it on various backends. So this one also might be a bit popular for the companies are doing the implementation through hardware platforms only. Being a researcher, we barely depend on the software simulators, but the companies, when they want to give a real-time solution, they have to depend on the hardware platform. That was IonQ, Regity, and QEra. Actually, it offers a high performance simulators like state vector and TensorFlow. Next is IBM Quantum Platform. It offers a fleet approach. You can simulate the circuits and then seamlessly run them on a real superconducting processor like 156 qubit Heron. And then Azure Quantum, it's similar to Bracket, integrated to the Microsoft ecosystems and notable for its recent world record in creating the logical qubits. It's error protected qubits. That's a main specialization of this. As of 2025, the landscape has shifted from single circuit testing to the utility scale simulation, where researchers use a hybrid classical quantum workflows to solve the real world problems. So now we are moving on to the quantum simulations. So in the simulation, right, the first three things are either IBM, Google, and Zandu. They are open source simulators. You would be able to freely do your testing. And again, based on best for quantum machine learning or NISQ research. So based upon the application or what research you want to do, you can select. But most of them, everyone, they suggest to start with QisKit and IBM. And QisKit AR is the one little bit advanced one than QisKit. And then the next couple of things is cloud-based Amazon Bracket and Azure Quantum. That already we saw both. Since its simulation is also there, that's what put it over here, cloud-based. And QLAX, QNA system by QNA system, and Intel Quantum SDK. It's a full stack simulator, and NVIDIA quantum, and quantanium is a hardware plus simulator. So both it has. So and the key features are I don't want to give much, but I'd like to show that how it is being best for what kind of applications you want to do research. So you can select it. So here one more comparison is it's based on whether it's like analog or digital. So analog is, for example, QisKit IBM, and digital, and analog is Locad and QERA. And what was actually the digital rate, it works based on the number of gates, how Hadamard gate or CNOT gates to build the algorithm. But the analog rate, it is basically it's based on the physical system architecture, how we implemented that physical architecture in the picture what we saw. And scalability, right, better for it's limited because in software realization, better for large scale physical simulation, and ease of use is like a classical programming. It's requires the understanding of physical Hamiltonian. Then only you would be able to like implement or grow with the analog system. And mainly used for digital system is finance, cryptography, and chemistry. And this is condensed for matter, physics, material science, matter, and optimization, and so on. So now, how these simulators, either software or hardware, are being used? Based on the literature study, what we have observed from the various research paper, the thing is right, a hybrid approach. First one is a classical, it's a digital emulation, and then the next one is it's a hardware implementation. And first they test the basic system using the simulator, and then implementing the thing with the hardware. So they are hybriding both software as well as the hardware. So the real world execution, right, it's based on both software and hardware. Someone, could you please mute your mic? Mr. Rajesh, sir, could you please mute your mic? Okay, I think he is muted. So here the focus of the quantum error correction research, right, it's based upon the Nexus quantum error encoding and error correction. And as I said, I'm going to mainly focus on the quantum error correction part, not in the encoding part. Here the main focus of the quantum error correction research, right, based on the either the resource optimization, it's reducing the physical qubit record for logical qubit, and then the how to reduce the overhead in LDPC, low density parity check code, and the coding whatever we are using for the quantum encoding, and efficient syndrome. So this is the basic thing, is resource optimization. Another one is we are giving the intelligence, artificial intelligence for error correction. And next thing is the logical qubit stability. And then next is a new quantum error correction architecture. It's based upon the neutral atom system and superconducting circuits and topological error. So these are all the various focus. So based upon that, the research papers. So don't, it might be person to person or researchers to researchers, it may vary. Some of you people who already done research on AML, right, you may, quantum machine learning part might be much interesting, and especially quantum error correction, right, people are researchers from the background of physics and EC might be a bit interesting. So others may be a little bit bored. But thing is, right, please try to understand that how the things are being, the research are being carried out. If you see the first paper, it's a AI-based quantum error correction decoder. As we said in the last slide, so AI for error correction. So they are adding the intelligence AI, and so the key findings are, if I explain, it's since I need to cover all those things, I could not like explain all those things. I'd be able to like highlighting the part. So AI based. Next one is suppressing quantum errors by scaling a surface code and a logical qubit. So here right, like again, they are concentrating on the coding part, and next is right fault tolerant. Again, they are concentrating on the error logical qubit, and then the reducing the optimization, resource optimization. So this is the way the LDPC code, other things are right, surface code logical operations, and then other couple of papers are in the low density parity check codes, quantum for that optimization. And finally, the experimental demonstration of quantum error correction neutral atom, right, that falls under the category of new QEZ architecture. So this is the way they are continuing their research. Still, the codes are being evolved, and then optimization on part of resources becomes much important. And one more thing is, when we go for a quantum, right, the energy consumption by the computer or CPU or supercomputer, when we compare, the quantum computer definitely takes more energy. So the power dissipation is also right, it would be high. That's what, again, the cooling part, that and all, that is also hardware part. Again, that kind of research is going on. I did not touch on this part, but how we can the encoding and these and all, right, this hardware platform, right, how we can reduce the power consumption. In that angle also, the quantum error correction and encoding part is research is going on. That's what I observed. So use the surface code, LDPC codes, and AI-based decoders and logical qubit, etc. However, the focus is right to build a fault-tolerant quantum computers with stable logical qubits and reduce the quantum error correction resource overhead, achieve the real-time autonomous error correction, and develop a scalable quantum computing architecture. So how the architecture can be scalable, so that is also much more important. So again, what would be the research direction? So again, based on those four categories only, and how this can be focus area, how this can be areas can be focused. That is also we observed, what we observed is presented here. Next is we are moving on to the quantum algorithm. So once we move on to the quantum algorithm, right, it's some of you wondered, even quantum optimization is algorithm also used for providing solution for applications, and quantum machine learning is also used for providing solution for various applications. So why two things? So both are quantum algorithms only. Here, the aim of the quantum optimization algorithm is to find the absolute minimum and the maximum. When you talk about the optimization problem, right? So the optimization problem is to find the maxima and minima to identify the gradient descent and all those things, right? To identify the peaks and where the gradient descent, its minima occurs and all. So to optimize the solution. So once you optimize the solution, you would be able to provide a solution for your problem. But when we compare with the quantum optimization algorithm, the quantum machine learning algorithm, right, the purpose is they supposed to learn a pattern and classify the data and generate new samples using the quantum enhanced models. So that's the main classification difference between the quantum use of quantum optimization algorithm and the quantum machine learning algorithm. So here the quantum optimization algorithm, right, either variational quantum eigensolver, most of the basic very beginning what we discussed and saw was quantum approximate optimization, QAOA algorithm and VQE, and quantum semi-definite programming solvers, quantum Hamiltonian descent, and a quantum central path method. So these are all the optimization algorithms. And the major quantum machine learning algorithms are quantum neural network, quantum convolutional neural network, quantum kernel methods, quantum support vector machine, and quantum generative adversarial network, and then quantum topological data analysis. But the basic things are quantum neural networks, quantum classical neural networks, and quantum support vector machine. So these are all the things. Now we are moving on to the quantum optimization algorithm. Okay. So it is designed to solve the optimization problem to finding the best solution among many possibilities. So it's faster or more efficiently than the classical optimization algorithm. So it widely used in the logistics, finance, machine learning, and energy systems and cryptography. If you see that the application of papers, what we have in this, right? The algorithm and especially quantum approximate optimization QoI, right? Major applications are traveling salesman problem, max cut problem. So these kind of things, and quantum variational quantum eigensolver, right? They focus on the molecular optimization. So here, when you see the quantum annealing D-wave, right? Again, it's analog based. It's supply chain optimization, machine learning, and financial modeling, and adiabatic AQO quantum optimization, right? It's constrained satisfaction problem. So here, one good thing is, right? So you would be able to, like, based upon the literature study or the theoretical knowledge, right? You would be able to identify like what kind of algorithm you need to select for what kind of applications. So, and why these algorithm, what are the advantages behind it and all, right? It was presented here. I'm moving on to that again further. So these are all the recent research papers on quantum optimization algorithm. So these are all the papers, very recent paper, comparative study on quantum optimization technique for combinatorial problem. The main purpose of quantum, moving on to the quantum, is to solve the combinatorial problem only. Next is challenges in here, right? Like first one in benchmark VQA, and these are all the quantum approximate optimization algorithm. These two are being tested. And so if we take the key findings and the contributions, you would be able to like see that the main algorithm, whatever, right? We discussed in that previously what algorithm. So these algorithms are being tested for various applications. Second one is, right, it's for dynamic satellite routing, and the third one is for ground state approximation. So based upon that, for various applications are being tested. So apart from that, right, the basic traditional algorithm, it was evolved during the initial quantum computing, right? These are all the new quantum optimization algorithms we found. Feedback based algorithm quantum optimization, and quantum singular value transformation, and recursive quantum random access optimization, and analog Hamiltonian simulations, and alternating direction method of multipliers, variational quantum non-orthogonal optimization, variational quantum, and quantum inspired clustering. So these are all the, so similarly, when you do any modification on the existing optimization and for providing the better solution for any applications, then you can evolve a new, your own quantum optimization algorithm. However, the focus is, right, again, it's to provide a solution for your own application. But the selection based on this, as you know, when you able to like identify for this kind of application, what would be the best suitable algorithm that was already it was being tested, so it was given. So you take that algorithm and do the optimization or like do the modification on the algorithm and come up with your own new algorithm. So this is a way the optimization algorithm research is going on. And one more thing is, it's the applications given are limited. So when you have like your own application that falls under the category of some specific type of application, then use that particular algorithm and test it. So this is the way the quantum optimization algorithm research is being going on. Next one is, what is the future directions in quantum optimization algorithm focus area, right? Reduce hardware requirements and overcome the noise and decoherence, because coherence and decoherence, a small picture I will show you in the last step. So while encoding and decoding, right, it goes into wrong. So decoherence. So it's focus areas to handle the large real world problems. That's what I said. When you take your own problems, when you like test with like some optimization algorithm, you would be able to get some solution. But when you do some modification and if some algorithm is being performed well, then that's a focus areas for a specific real world, large real world problems. and similarly efficient training of various algorithms and combine more than one algorithm. When I observe almost in most of the research, either in quantum security or in quantum optimization algorithm or in noise error correction, everywhere what I observed is a hybrid approach. So hybrid approach, more than one thing you add and come up with your own solution, and domain focused solution and demonstrate the performance of the benefits and advanced theoretical approaches. So this is the way you can focus your research and come up with your own solutions. Next, we are moving on to the quantum machine learning algorithm. And quantum machine learning algorithm, right? So first we need to understand why QML outperforms than the classical machine learning algorithms. Because right, when we go for NP-hard problem, combinatorial optimization, right, this heuristics like G and PSO simulated and annealing scale was its poorly. So the quantum QAOA and quantum annealing map the optimization directly to the Hamiltonian. So you would be able to get the faster convergence for NP-hard problems. And next one is temporal and sequential learning. So classical LSTM, right, suffers from vanishing gradients in long horizons. But quantum LSTM, right, it utilizes the entangling layers to maintain the coherent and predict with the fewer parameters. So the next is, right, it's high dimensional data. Even that's what either the data is huge or the application, especially on multimedia based image or like video based applications, then the classical even system with the GPUs also, it's failed to, it takes quite a long time to predict the answers. So when we go for high dimensional data, then we need to go for quantum. So these are all the way our classical machine learning algorithms fails. So now we move on to the core QML architectures, right? That's what very beginning I said. Quantum neural network and convolutional neural network and variational quantum circuit VQC and quantum support vector missions. So these are all the each algorithm, how it works. I think, hope you remember that the building of quantum neural networks, how the I think both Aarti as well as Karthik Ganesh discuss about these two things. How it is being from the classical data and how we are converting into the quantum data, and then how the neurons are being built on the qubits. So this is a way QNN start implementing, and then quantum convolutional neural networks and so on. So this is a picture, classical data, and do the encoding. So once you get it right, so you are doing the parameterized quantum circuit. With that, right, you implement the neurons, neuron layers, and quantum neural networks, and finally you will get the provide solution for your applications. So the major QML application, quantum machine learning, right? If you are a machine learning researcher, AML, data science in this field, right, you would be able to know how it's vast. It's, I would say, it's like an ocean. So the applications, right, evolved whatever, right, it would be very huge. But however, I'm limiting with 10. I took 10 applications. Out of 10, I'm going to discuss about around 5 applications. One is drug discovery and healthcare, and next one is financial services and risk analysis, computer vision and image processing, and natural language processing, climate modeling and energy systems, material science, autonomous systems and robotics, recommendation systems and big data analytics, optimization problems, and cyber security and cryptography. So first, second, third, fourth, and finally 10. So 5 application part we are going to discuss in further. The first one is for the QML for drug discovery. So most of the pharmaceutical companies, right, they are working towards providing solution for drug for specific disease. So if I'm able to see that from 2024 to even 2026 also, I saw a couple of papers, but somehow even between 23, 22 to 25, these many papers we found. So really, the pharmaceutical company, they started working on it, and moreover, like bio-based researchers, right? Biotech researchers, right? They are really they are much interested in working for providing solution for identifying the new drug. So, quantum machine learning framework for predicting the drug sensitivity in multiple myeloma using protonic data. So, to identify or like predict the drug sensitivity, how it will react. So that and all also it is possible to like do that with quantum machine learning applications. So when you are interested in the field of biotech and providing solution for the drug, then you are suggested to like see these kind of papers. So here approach is right. Like a Q-proto machine learning framework using the protometric data and quantum LSTM model, quantum neural networks, and variational. If you see that, almost classical, and some of the new algorithms, quantum machine learning algorithms also we found evolved for quantum machine learning for drug discovery. And next is we move on to the quantum for healthcare. So in quantum healthcare, we would be able to see now only more research is going on. Though we have like around 6 papers only, we have took it for discussion. Again, I don't want to explain much on that. The first one is Asthma disease early screening model, and second one is blood glucose and HbA1c estimation model, and the third one is lung cancer. So this is the way the algorithm what they have, quantum machine learning algorithm what they have selected, and what performance results comparison compare with the classical SVCKNN or basic model, what like they found it. So based upon the results, what even we observed, right? When the data set is minimal, and moreover, even Aarti also quoted this one, if you remember, when the data set is limited, quantum machine learning outperforms than the classical. Because right in a single shot it will give an answer. So since your processor is able to like handle the like a data in parallel, it will be able to like do the prediction in a single shot, and then give a that is like a minimum number of steps only for prediction. But when you go for classical method, right, it takes the training, right? When you train the data set with like a large number of data set, then only your testing it would be like meaningful. Otherwise, right, you are testing some of the papers they come up with. We are having very good confusion matrix, very good sensitivity, very good prediction. That means like 99%, 100%. That is theoretically only it is possible. Practically, it is even for simulation also not possible. So when you test with a limited number of data set, and you again train with a limited number of data set, and if your testing also like falls under the same category of data, then it will predict 100%. Yes, it's correct. The disease is there or not. So it will say. So for limited data set, your classical method fails, and for limited data set, quantum machine learning outperforms. But when the data set is grows, then the classical model it will perform better. Why? The reason is the quantum machine learning, right? When your data set is grows, then the number of qubits also increased. When the number of qubits increased, then the that is the entanglement of the classical bit and superposition principle, right? That when it grows, then the decoherence for decoding part, right, it would be very complex. So that creates a quantum error, and because of the quantum error, it's when the application have more data set, it fails. So once if we provide solution for like provide solution for better correction, right? Then we would be able to like realize well at that time, right? The quantum will rule the world. So again, it's a short summary I have given. Finally, once we saw the like various application part, then I'll tell you like what are the new quantum machine learning algorithms are being evolved and all that I would like to say. Portfolio optimization is also one of the main area nowadays, because right, share market today, many of the business people, right, they invest money through share market. That is much more important. The prediction, right, it's very, very, very important. Even one of my student, third year student, he has provided a solution, and he has implemented in real time also, and he has given a solution for one of the portfolio company, a finance company, fintech company, and that solution was being realized in real time also. So that's what I asked him to give a small demo on his whatever the development he has done, the quantum machine learning for portfolio optimization. So next is the quantum machine learning for NLP, natural language processing. So here also, again, as I said, hybrid approach is being tested in the first paper, HQML, NLP, a hybrid quantum machine learning framework for scholarly AI text detection. Again, the NLP application, right? When you take natural language processing applications nowadays for both AI and generative AI, you would be able to like see so many number of applications. But the application what tested right now in quantum, right, it is very limited. So if you see the number of papers what we have found in last few years, right, it's limited compared with the security, quantum NLP and computer vision. First one is a hybrid quantum, and second one is a variational quantum circuit and quantum kernel similarity. And third one is a pre-trained quantum context sensitive word embedding for NLP, right? It's for quantum word embedding and context matrix. So what paper and what methodology they used, and finally the key findings also presented here. So comparing natural language processing and quantum natural language processing approaches. So again, they also like using the quantum circuits, and these are all the quantum NLP, Lambert toolkit. So these are all the again similar kind of methods used for NLP. Next one is we are moving on to the quantum machine learning for computer vision. So again, computer vision also we have nowadays what we observed even last 2025 and 2026 also we found one or two papers only. These are all the papers like we saw 2 or 3 years before, from 2020 to 2023 we would be able to like see. And main application is based either image generation or pattern recognition or classification. So these are all the thing, and paper and what they worked for it, and what machine learning algorithm used and all, right. So if you observe that, you would be able to like see. So many number of computer vision applications are right now it's being tested for generative AI applications. So those kind of applications can be realized for quantum in future. So the new quantum machine learning algorithms evolved from the traditional what QNN, QCNN and all those things, right? So these are all the new QML algorithms evolved that and all what we observed. First one is a quantum diffusion model, and that was evolved from the classical stable diffusion and GAN, and quantum graph neural networks evolved from QNN, QCNN, and equivariant quantum neural networks, it's evolved from the standard variational quantum circuit PQC and QCNN, and quantum reservoir computing and quantum federated learning, and geometric quantum machine learning, and evolution from the equivariant QNN, and quantum reinforcement learning and hybrid approaches. So this is a way either you can modify the existing neural networks and then come up with a new quantum algorithm, or go with the hybrid approach and select what applications you want to like a test, whatever, whether it's like NLP or computer vision or like a healthcare or drug discovery, right? So first you identify what application you want and then test with the existing classical quantum machine learning algorithm, and based upon the quantum algorithm, what the new quantum machine learning algorithm evolved. So if you see that the incremental research what they have done, so once you are able to like understand, you would be able to like come up with your own new quantum machine learning algorithm, as well as you can implement for your own application. So this is the way you can take it into the like a new direction. So this is the way quantum machine learning algorithm researches can be carried out, extended in future. Next, we are moving on to the quantum cryptography. So quantum cryptography, right? Already Darshana told that Shor's algorithm, right? It is easy to like normally when you study about being a student, when you study, for a student, if you ask RSC and ECC, they will say it's a very complex and more secured ECC, especially elliptical cryptography and all. But when you go into the quantum, right, because the permutation combination, what it will put is the quantum, it easily put it in a single shot and give a crack the key. So Shor's algorithm, Shor's Groovers, and these algorithms, right, already it was demonstrated that easily breaks RSA and ECC keys. So Groover reduces the symmetric key security by root n and harvest now and decrypt later. So what the intruders they will do, right? They will take the dump of the data, and then later on, once the quantum evolved, they can test with like a quantum and easily crack the key. So that's what now itself the companies are really worrying on the security part. Now itself they want to implement the quantum security. That's what quantum security is given much more importance by the researchers as well as the company. So long life cycle data at risk, healthcare, is defense and finance, these and all, right? Much more very sensitive data, these data. So emphasis on migration urgency before the fault tolerant that quantum computing exists. So before the quantum compute comes, we need to provide a solution. So otherwise, right, the intruder will take the dump data dump, and then finally they later on they will analyze and they identify the key. So that's what. This is the era and basis and risk level, right? Classical, right? It's integer factorization and it's quantum vulnerable, and post-quantum, right? Quantum resistant, and quantum cryptography, right? It's one is it's a hard mathematical problem, and another one is physics-based security. So information theoretic. Here, post-quantum security is not equal to the quantum cryptography because, right, PQC runs on the classical hardwares, and quantum computing requires the software. Next is post-quantum cryptography, and post-quantum cryptography in Darshana's discussion also she told, hope you guys remember that she tested the Kyber. So standardization was done by the NIST, and the various PQC categories are lattice-based, code-based, hash-based, and multivariate and isogeny-based. Here, out of 5 post-quantum cryptography categories, right, the lattice-based performs better than the other because of the strong worst case to average case reductions and efficient key size. One major complex in quantum cryptography, right, it uses the large key size, but here the lattice-based use efficient key size. That's important here, and fast operation and balanced security and performance trade-off. So this is the one of the direction for research. Even one of my PhD researches also I implemented the IPsec security at layer 3, and I tested the performance because when you add a security, it will add the overhead. So when overhead is being added along with the regular data, then the performance of the system will get degraded. Yes, still though the performance is degraded, then based upon the application, when your application is more highly sensitive application and you no need to worry about the performance, then go with that. So in 2022, the post-quantum security, like cryptography securities, right? These are all the things, Kyber and Lithium and Falcon and switches. These are all being selected by the NIST. And finally, Kyber, right, it outperforms than the other security algorithms. So still the research is going on. Next is the quantum cryptography with the hybrid cryptography approach. Even in last Saturday discussion also, like she tested, Darshana tested with a hybrid approach for tele company. So here the quantum security, right, is derived from the physics. It uses the superposition and measurement disturbance principle and no cloning theorem at all. So here the major quantum cryptography techniques and all, right, quantum key distribution and quantum random number generation. Here the quantum random number generation is right, practical and commercially available today. Commercially it's available right now. Quantum secure direct communication and device independent cryptography. It's still in the research stage. So here the single what we observed is even in last day discussion also we would be able to like observe that single layer security is very risky. So they go for a hybrid approach. In a hybrid quantum security, right? Classical, they add the classical and post-quantum cryptography and quantum cryptography approach entropy. And the benefits of quantum cryptography are it's like backward compatibility, quantum resistance, and entropy reinforcement and defense in depth. So hence, hybrid model is now under research and as well as being implemented or tested and implemented. So here the proposed architectures, right, like PQC KEM and Cure RNG, and then entropy based. So these are all the various hybrid approaches. So if we like if you want to like see more, then again it's get bored. So here what I would like to emphasize, right, if you are researchers in the field of security, if you see that the network contest, see that in what contest they have tested. So various type of networks, software defined network, public internet, private and wireless backhaul network, classical network. If you see that IoT network, so various network is the one of the major contest for which network you want to test the your quantum security, either PQC or QC or the hybrid approach, and then domain, which domain you want to do that. So these are all the parameters. It will whether you want to do the authentication or authorization and what kind of guarantee you want to give. So these are all the various parameters that will play for quantum cryptography and quantum security research. So that's, as I said, so much of papers are being evolved. Even it was research was done, as well as some of them are in implementation stage also. So this is the consolidated inference of the quantum security. The post-quantum cryptography as a transition from theoretical research to the standardized implement with ML, KEM, Kyber. And last session we observed that machine learning DSA and SLH DSA, and formally adopted by the NIST. And lattice based constructions are being currently provide the most practical balance between the security and the efficiency. As I said, when you increase the security, the efficiency or the performance of the system, right, get reduced. So that need to be highly taken care. And algorithmic diversity remains critical. So that inclusion of HQC as an additional KM highlights that need to be avoided. And then the next is quantum cryptography, particularly QRNG, and enhances the entropy quality and strengthens the hybrid architectures without requiring the full quantum communication infrastructures. So the hybrid cryptographic models are classical, as I said, combination of three. So it's mainly offer the defense in depth security and provides a backward compatibility and reduced migration risk. You can easily move from your classical network environment to the new network environment, and practical deployability for RTC and IoT systems. and based upon the performance analysis, right, it confirms a overhead and symmetric encryption dominates the cost for large data, and the proper key derivation is much important. It should be like a very robustness. So the future direction of the quantum security, right? We need to concentrate on the lightweight post-quantum cryptography for constrained environments. So based upon the environments, for example, optimization of MLKM for IoT and embedded devices, and memory efficient implementation is also much important. Suppose if you are, want to like implement your security part for the small embedded system, then the memory is also another constraint, and constant time and side channel resistant libraries, and advanced hybrid key derivation model. So how you are deriving the key, standardized integration of QRNC, and formal security proofs for entropy cascading, and side channel and fault resistant and quantum enhanced infrastructure. So, and how, what kind of network you are using on it. So overall, the quantum research, so whatever we discussed so far, right, actually very sorry, because if I explain all those tables in a very detailed manner, some of you get bored and some of you get interesting. So just I'm highlighting the points only. So honestly speaking, these literature study was done by my UG students only. They are really interested in working on quantum. So finally, the overall inference, right? Whatever, whether it's like encoding, error correction, or quantum optimization algorithm, or quantum machine learning algorithm, or security part, this is the future directions in a nutshell. So the more research works are going on quantum encoding and error correction as a quantum, because right, as quantum error correction is a bottleneck. Especially chip manufacturing companies and researchers with a background of physics and easy are working on it. Even while we are taking the paper, we used to see like from which like R&D lab this paper come out and all, either company or with labs from the either the physics or especially chip design, that easy researchers. So researchers with the background of optimization technique, mathematics people, right, as well as some of the people, those who are interested in math, right, they're working on quantum optimization algorithm, because they see that what are the classical optimization algorithm and what is the algorithm, how these algorithms are being tested for their application. If your application falls into the same category, then you first test, take the application, test the existing quantum optimization algorithm as well as the new incremental new algorithms evolved, and then you come up with your own new algorithm. So, and compare all those results and present a paper. So this is the way they are moving on it, and quantum machine learning is a major area to explore, because right, the drug manufacturing companies are really, they're working for so many things, so sensitivity of various properties of the drugs, how it is being, and especially for the specific symptoms. Nowadays, right, even our traditional tablets, some of the tablets, and are right now even for normal cold and fever also, that doesn't work out. So we need to go for the latest drug found out with the companies, right? So the same way, drug manufacturing companies are really much interested in providing solution for specific like symptoms as well as for the applications. So next is healthcare. In healthcare, right, disease prediction shall be extended for other diseases. If you see, especially for AML, right, even deep learning algorithms, right, heart disease prediction, if you put Google it, then you would be able to like see more than 100 papers, especially on machine learning and deep learning. You would be able to like see more than 100 papers. But here, the disease, the tested for quantum with the tested with the quantum machine learning, right, limited. So if you are a new researchers, right, you please concentrate on different disease and then try to give a solution. So that's a way you can take your research for future. And similarly, quantum NLP and computer vision also can be extended for other applications. You will be able to like nowadays, because right, AI itself is ocean. So whatever we tested in a traditional classical machine learning deep learning models, so can be tested for again for the with the quantum. So again, one more thing is quantum generative AI is also right now started. The research is going on. So these are all the major areas to explore quite a lot for the researchers. So if you are a researcher and try to learn and then learn how to build a like a qubit and provide a quantum Fourier transform and all those things, and give a solution with like a minimal number of qubits, 2 qubit, 8 qubit, and then go like a to the power n, and then build a quantum circuit and test with your own like a data and see how like your like a quantum circuit perform. Similarly, since the security is a major concern because of the quantum evolution, and more research efforts were done. However, the quantum security shall be extended for different network type, because whatever the network type, whatever it's available is again I would say limited, because nowadays you can see even personal area networks also like it can be, because in healthcare we barely depend upon the personal area network, right? So even in that way also can be your data can be hacked. Next is a combination of hybrid architecture and optimization on security versus performance. So this is a way you can take your research into the next future directions for the quantum. So short presentation is going to be presented by student for portfolio optimization. Santosh, are you in line?
Yes, sir, I'm here.
Yeah, could you please, I'll stop my sharing so
Yeah,
that
yeah.
you please.
Yes, sir.
Yeah.
So, good evening, teachers. So, as Perumalraja sir told that I'm working on. I have made a research on quantum portfolio optimization. So, I will just share my screen and show how I implemented. I haven't went like very deep into the thing. So, like I will just show you the outlines and a basic implementation of the whole thing. So, yes. Actually, what I have did here is we all know about this trading and stock market things. So let's say a portfolio. A portfolio is always something where you have a bucket of stocks. So let's say we have three stocks. So here I mentioned here n is equal to 3, which means like I have three stocks. And this is mu is here the returns, the percentage of returns. So if I pick stock 1, the return is 15%. If I pick stock 2, the returns is 20%, and stock 3 is again 15%. So I have mentioned the return percentage as a number in this way. The next one is sigma. It is a covariance matrix where I have the uh, like kind of risk. So let's say 0 point, like the diagonal one, the 0.05, 0.06, and 0.07 are risk if I pick only the stock itself. So let's say I'm picking the stock 1. So for picking stock 1, I have the risk of 0.05, and risk of 0 point, like risk of second one is 0.06, and risk of third one is 0.07. The diagonal one represents every single stock here, and off diagonal one, so let's say this one is the combination of first asset and second one. If I pick two assets from this portfolio, and what is my risk percentage? So it is very meaningful, like 0.01 percentage. So if I pick asset 1 and asset 2, my risk will be very low. Same applies to all. So if I pick asset 1 and asset 3 together, my risk will be 0.05 again. So this is how I have made my input data. So with this, the quantum things will start. So I will just run this thing and I will show what are the steps it has gone through.
Santosh, you may tell about the what kind of data you are feeding. So because right, like
Yeah.
that's much important.
Okay, so actually, like right now, I'm using only 3 stocks, and the data used to calculate this. I haven't shown every data here. Like I have pre-calculated and given here. Usually in my research area, I have used the
But the
like
data what you used is a real time data, right? Where you took it, that also
yeah,
you,
yeah, yes, sir.
yeah,
So I have taken 3 real-time Apple, Microsoft, and Google. Three
yeah.
real-time stocks. I have computed its returns and its risk against each other. So I haven't added those code here. It will be more confusing if I add like how to retrieve all those data and compute all those things. So I have just made this alone, this part directly, but in my research part, I have made the whole thing. So you can directly connect the stock market to the quantum part. So using those pre-computed parameters like my expected returns and my covariance risk matrix, I can go for QUBO matrix. So QUBO is something like something which is made before quantum. It is a hybrid thing. So you should first compute it with the classical one. So here we do with the classical one. I will just explain what it is, so it will be very clear. So if you see this diagonal part, this diagonal, and this part, it will be in negative. So what it means is like if you pick just only one stock, the risk will be very like the one which shows here in minus is like the most minimum energy while picking the stock. Let me give in a very brief thing. If you take like a gradient problem, so a parabolic problem, you will see the highest point, which is the global maximum. So in the case of finding global maximum, you will reach the topmost point. But if I flip the parabola upside down and try to find the most minimum value in that, it will be equal to the same for the maximization where the parabola is up. So, so if I just turn this around and make it minimization problem, I will get the most minimum, and it is the same answer for the first solution. So what I have just did here is I will try to make my whole portfolio into energy landscape and try to find the most minimum energy landscapes. So this minimum energy landscape is the most global maximum. So it may be confusing when I say all these terms in a one go, but just let's imagine this like a
Santosh, you may just a high level picture is more than sufficient, because when
okay.
they're really doing on research on that, right, then a more micro level things need to be recorded. So how it is being the data. So as I said, so what company you have taken, and how the data is being fed, and how it is being how the quantum performs compared with even classical. So that's highlight of
Yeah,
this.
yeah.
Yes.
Okay, so like basically from QUBO, we will get the most maximization portfolios. So if you see like here we have minus 4.17 is the most minimized number in this whole thing. So what it means is if you pick just second one, it will give more returns and less risk. So we can just see here the expected is more high here. So just to make people understand, I just took three stocks, and in this 3 stocks, the most highest return is the second one, and the second one has the most least number, which means it has the highest like returns. So in the energy landscape, it will have the most deepest landscape. So using this, I will run the QAOA, which is a energy like quantum energy energizing. It will search for every possible combination in the whole search area and find the best combination in the whole thing. So I have told the quantum portfolio to exactly pick 2 assets from the given 3 things which I can invest. So so the quantum thing has told me something like this. So most profitable portfolio is 1, 0, and 1. what it means is I have given three stocks and it has told me to pick first one and the last one. Don't pick the center one. So it means if you go for a single, if you want to pick and invest only in one stock, you can go for the center one. But if you want to invest in two things and you want to grow two stocks together, don't pick the second one. It will not perform together with others, but the first and the second one will perform good together. So it will, you can see it will give a like very good expected result and a very good risk. So like if we like, it is a very small problem if we see for a three stock thing. Usually in stock market and kind of things, like we used to go more than 50 stocks. So it is really hard to brute force all those combinations and find the best portfolio. But if we use the quantum here, and it is really easy where we superposition every portfolio in one energy space and find the most maximization portfolio and just return that single portfolio. So yes.
Okay. So finally, inference, and for which company you tested?
I actually tested for Apple, Microsoft, and Google.
Okay.
So it asked me to buy Apple and Google. Don't buy Google, like Microsoft alone.
Yeah. So what the data set? How many years for you took it?
Like I just I just took for only 1 year, sir.
1 year. Okay. 1 year data set, complete data set. Okay.
So in a real time thing, like I used to go for 10 years or something like that. A
Yeah.
huge one I will go, and just to make it easy and simpler to look, I just went with small data.
Okay. Thank you, Santosh.
Thank you, sir.
Yeah. So almost that's all about. We are coming to the end of the session today, and so after that, yeah, nothing. Just a thank you only. So here, right, I am building a quantum research group. Suppose if you want to discuss in further on doing quantum research or anything, right, feel free to contact me, and we shall, if you want, we shall work together and collaborate ourselves. So that's all about today, and thank you so much. Thank you, CSC HOD sir.
Thank you, sir. Thank you, sir.
Thank you. Any questions, or we will close? See you again maybe in next year or after some time. See you guys.